I was just wondering, is it safe to say I can set a proctor date for Monday for the final exam?
Yeah, I'll make sure you can do it by Monday.
Okay, yeah, I just saw on the syllabus that I could do it by Monday. I wasn't sure if that was 100% true.
Yeah, I'm glad you brought it up because otherwise I was just gonna wait and probably have it till Tuesday. But you can do it any day this week. I'd prefer you to do it by Thursday, but if you do it Friday, you'd have to do it by noon on Friday, hopefully. But if you want to do it as early as Monday, we can.
Uh, I could do it. You're talking about Tuesday, yeah,
Yeah,
by the
Tuesday or
28th.
Thursday or Friday or Wednesday, any of those.
Okay, yeah, I didn't know if it was like a hard date like the 27th or not.
No, I like to have all the exams on one day, but this semester's been such a wash. I'm trying to be as convenient to my students as possible. So any day next week would be fine. Monday, Tuesday, Wednesday, Thursday, or Friday. But ideally, I'd like to have it done by noon on Friday. Uh, Even that's not a hard line. So if you want to do it Monday, just let me know, and I'll make sure I'm going to set up to try to have it the exam made so that you can take it on Monday. But if you're not taking it on Monday, let me know because that'll give me a little bit of breathing room to do it.
Okay, yeah, okay. In that case, I think I'll try to do go for Friday.
Okay.
Um, and I can do that. I'll see if I can take like a day off of work just so I
And you're
can do
doing it at
that.
a testing center?
Yeah,
Okay.
I'll see if I can do it Chesapeake. Last time I was,
That's cool.
but I'll send you the details. I'll get that in tomorrow.
No problem. I appreciate it.
Yep.
All right.
I thank you.
No problem. Thanks, Sam. Yeah, so it's now 5:37 p.m. Wednesday, July 22nd. I'm probably going to go since I started about 8 minutes late. I might actually go 8 minutes long, but you can leave at any time. You don't have to wait for me. I'm trying to knock out at least sections at least up through section. Let me check these section numbers real quick. I'm going to be in chapter 14, and I want to at least do the examples up through section 14.3. I want to make sure I get that done. And then tomorrow at 8 a.m., during our lab meeting, which is optional. It's a Q&A session in principle, but I'm just going to go ahead and cover chapter 15 at that time, and then, like I said, it'll be open to Q&A as well. I will be offering another Q&A, obviously on Thursday because I have a class that meets from 5:30 to 6:50, or excuse me, to 7:40. So I'll have that time, but I can also do a Friday. I might even do a Saturday or Sunday if someone requests, and then Monday. I'm doing a Q&A for my class that's face to face from 9 a.m. to noon, and I'm doing the same thing on Wednesday, but I can also set up other days if anybody needs. So those are all times that you can get help from me if need be. I can set up Zoom meetings, and if I do set up a Zoom meeting, unless you explicitly tell me you need it to be a private one-on-one thing, then anytime I set up one, I'll announce it to the entire class so that everybody can get help. But with that in mind, I'm going to go ahead and jump into chapter 14, if that's cool with you. You don't have any more questions? Okay. All right. So we are covering chapter 14, and chapter 14 is called uh, oscillations, and section 14.1 is oscillations in the spring, and 14.2 is simple harmonic motion. 14.3 is the energy of the simple harmonic motion, or yeah, simple harmonic oscillator. So I thought I'd go ahead and knock out the differential equations portions of all this to begin with, so I can get some of the equations that we'll need for the examples, and then I'm going to go ahead and work the examples. So in order to do that, I need to share my screen. Here I go, sharing my iPad screen. Now, hopefully it'll pop up. Yep, it's coming up. I've taken the time to go ahead and write out some of the initial stuff. We already learned about Hooke's law. F equals negative kx is Hooke's law, but you got to remember when the negative is in there, that's the force. uh, exerted by the spring. And if you say F equals kx, that's the force that has to be applied to the spring. And remember, this is Hooke's law, and we mostly use it for springs, but in reality, it's applicable to 2x4s, to iron rods, even to ropes. If you actually, as long as you're keeping it stretching the rope as opposed to compressing it, but it works for compression or stretching when you're actually using an object that is solid, like a iron rod or a 2x4 or something like that. So this equation is actually applicable. We just normally focus our attention on springs because it turns out that in order to measure the actual distance that something is compressed or elongated, if the object's a solid, rigid object, that normally takes such a large force that it's actually kind of dangerous. So that's why we just sort of stick to springs when we're doing it. But anyways, that's Hooke's law, and I've written down Newton's second law: the summation of forces equals mass times acceleration, which really is a vector equation, but we're talking about one-dimensional motion right here. So I'm going to go ahead and ditch that three-dimensional aspect and just say we're doing the summation of forces in the x direction equals mass times acceleration in the x direction. And in this case, this is one of the instances where the mass isn't changing, so F equals ma is okay. You don't have to use F equals dp dt like we learned is the more general version of Newton's second law, but the acceleration is going to actually be a non-constant, and because it's not a constant, you actually have to use a is equal to the second order derivative of x with respect to time. You could use a is equal to dv dt if you wanted to, but we're going to solve it for x, so we're going to go ahead and use it as d2x over dt squared. And we use Newton's notation when we're doing this just for ease. Specifically, what that means is when you take a derivative with respect to time, you just put a dot over it. So you can see in this case, I've got a dot over the x, but it's two dots, and that's because it's a second order derivative. So if I wanted the velocity would be x dot, but the acceleration is x double dot, like that. So now if we apply Hooke's law to this F equals ma, we get negative kx is the force that the spring applies is equal to mx double dot. I can go ahead and put all those terms on the same side, and that's what I get here. Mx double dot plus kx is equal to 0. But it turns out it makes a little bit more sense and is easier to deal with if we multiply by 1 over m on both sides. So when I do that, I get x double dot plus k over m times x is equal to 0. And this is called the simple harmonic oscillator equation. That's it. Basically, the general form is a second order derivative plus a constant times the zeroth order derivative is equal to 0. That is the fundamental simple harmonic oscillator. So whenever you see that equation, you should immediately know, I know the solution to that differential equation. And the solution, if you were taking differential equations, they try to make a point that this is clearly something that would be helped if, for instance, we had a function that if you took its derivative, it out would pop the original function times some value. That's called an eigenvalue type thing. You might learn that later, but the main thing is if you take a derivative of something, some function, and you get some number times the original function, then that's sort of an eigenvalue derivative. So functions like that, because this equation is x double dot plus something times x is equal to 0, any function that does that would be really, really useful. And we know that e to the rho t, for instance, if you take the derivative of that, that becomes rho e to the rho t. If you take the derivative again, that becomes rho squared e to the rho t, and so on and so forth. So e is a really good choice there. We're not in a differential equation class, so we're not going to do it that way. What we find a little more physically reasonable, even though it's a little bit weird because when I take the first derivative of this, it won't come out to be exactly the same function we had. It's going to be the same function with a slight change. Specifically, if you assume the function is going to be sine, then the derivative of it's going to be cosine. If you assume the function is going to be cosine, then the derivative of it's going to be negative sine. But it turns out to work either way. And really, using Euler's formula, e to the I theta equals sine theta plus I cosine theta, that really allows you to convert the e to the rho t back to sines and cosines if you wanted to compare that, what you did in differential equations or what you will do in differential equations, to what we're doing in physics. So what we do instead is in physics, we let x equal to a cosine omega t plus phi. And I was just in the process of writing all this up, and I wanted you guys to understand it. If you remember, a derivative and an integral are opposite operations. So you can take the derivative of something, and then if you want to undo it, you integrate it. Similarly, if you take the integral of something and you want to undo that, you can take the derivative of it, and you'll get back to where you started from. So in that sense, they're opposite operations, and that's part of the fundamental theorem of calculus. Now, if you think in that and in terms of that, then you realize a single derivative can be undone with a single integral. And normally, if you integrate a function without actually having limits of integration, you have to introduce an integration constant. You probably remember that from calculus. Similarly, if you actually have two derivatives, in other words, a derivative of x with respect to time is velocity, and then you take the derivative of the velocity with respect to time, then you get a second order derivative. So that's going to take two integrals to undo it. So just in terms of that idea, it does seem reasonable that a second order derivative, differential equation in this case, x double dot, is going to require two integrals, and that would produce two constants of integration. And that's pretty much correct. What it means is there's going to, in order for you to estimate a solution for this differential equation, since it's a second order differential equation, meaning the highest derivative is an order of two, then you're going to have two integration constants. So any function we make up to be the solution of it has to have two variables that are unknown, and then we're going to use the initial conditions to figure out what those unknowns are, just like we use the initial conditions to get rid of the integration constants when we're deriving the kinematic equations. For instance, we integrated the constant a is equal to dv dt, and that gave us at is equal to v plus some constant. Well, if we said that v equals 0 at t equals 0, then that would mean the constant is going to be 0. But if we said v equals v0 at t equals 0, the constant would turn out to be like negative v0 or positive v0, depending on where you put the c. So that's how you get rid of these constants that pop in there, is from the initial conditions of the problem. So when I say in physics we let x equal a cosine omega t plus phi, the a and the phi are like the two integration constants, but the omega turns out to be a property of the differential equation itself. In fact, it's going to depend on the constant. Remember, I said the general form of the simple harmonic oscillator equation is a second order derivative plus, it's critical, it really needs to be plus a constant times x. And I say it's sort of necessary to be a positive, but the main thing is this definitely has to be a constant there, and then a zeroth order derivative. So what I'm telling you is this omega is going to be turn out to be dependent on that constant right there, and you'll see it in a second, because all we have to do once we guess a solution to a differential equation is we got to take the derivative of that solution and plug it in the differential equation and see what works out. So that's what I'm going to do now. So now that I have that, then I can say x dot, which just as a reminder is dx dt. And just as a reminder, dx dt is velocity. So I had a x as a function of t. That's the a cosine omega t plus phi. And now I've got a x dot, which is v as a function of t. And I get it by taking the derivative of that function. Well, if you take the derivative of cosine, you get negative sine, but then you got to take the derivative of the argument of the cosine with respect to time. The argument of the cosine in this case is omega t plus phi, and phi is a constant and omega is a constant. So when you take the derivative of omega t plus phi with respect to t, you get omega. So this derivative is going to give us negative a omega sine omega t plus phi. So that's the first order derivative. The second order derivative, x double dot, is going to be dv over dt. And that, of course, is equal to a of t. Now, in this case, we're taking the derivative of negative a omega sine omega t plus phi. The a and omega, just like the a before, is just a constant. So that just comes out in front. So the negative and the a and the omega is all going to stay there. Negative a omega. I'm going to leave a little space after the omega because you might have already guessed what's going to happen, but I have to have some room to do something with that omega. Now, the derivative of sine is just cosine, and then I got to take the derivative of omega t plus phi, and that's going to give me another omega. So that's why I was saying I was going to leave a space, and now we have cosine omega t plus phi. So that is actually the acceleration as a function of time. Now we can plug that into the differential equation. So I'm going to say plug these into the simple harmonic oscillator equation. When I do that, you can see what's going to happen. I'm going to have negative a omega squared cosine omega t plus phi. That's for the x double dot term. Plus, I'm going to have k over m, excuse me, yeah, k over m. That's the constant that we had right here. And now I've got to multiply that by just the plain x, which is a cosine omega t plus phi, like that. And that's the whole equation, except it's equal to zero. So now I got to say equals zero. Now, what we see is this is the exact representation of Newton's second law. That means it's got to be true at all points in time. Since it's got to be true at all points in time, I can't really do anything with the omega or the phi, or for that matter, you really can't do anything with the a to make it true at all points in time. So what I'm going to do is just factor out the a cosine omega t, and what we then get is negative omega squared plus k over m, all of that times a cosine omega t plus phi is equal to zero. It has to be true at all times. And in order for that to be true at all times, again, I can't do anything with the a other than make a equal to zero to make that true. And that's a trivial solution that wouldn't be helpful to us at all. So we're not going to mess with that. So really what we've got to say is k over m. That's a really bad looking k. What we really got to do is take k over m minus omega squared, set that equal to zero, and what we get is omega squared is equal to k over m, and that means omega is technically plus or minus the square root of k over m, but of course we're just going to choose the positive version, so omega is going to be the square root of k over m. So as I said, the the omega is only going to be determined by the constant. We don't have to have any initial conditions for that. So now we know exactly what omega is. Omega has to be the square root of k over m, and then all that information we know about omega, frequency, the period, all that stuff is still in play that we learned from rotational motion and that we learned from the harmonic oscillator when we did earlier. So we also have, in addition to this, we have omega is equal to 2 pi f, where omega is called the angular frequency or the angular velocity, and it's measured in radians per second. Now it's normally measured in radians per second, but sometimes I will just call revolutions per second as if it's omega or something like that. It could go either way. That would be possibly F or whatever. So, anyways, I'll just leave it at that. But it's best if you want to just keep it straight till you learn what you can work with and what you can't work with. It's best to just say anything that's radians per second is going to be omega. Everything else is going to be F, and then we'll have F is equal to 1 over the period, or the period is one equal to 1 over F, and F is actually measured in cycles per second, which some older books will call CPS, but we've now adopted the hertz for that. So that's the the actual unit for F. So I'll go ahead and box that off, and I'll box this off, which is the same thing as this. And I'm not boxing off the units. That should be pretty self-explanatory. But the other thing that we're going to say is the period t is usually measured in seconds. So that's the units that we'd have for that. So we now have all this additional information about omega and then how it's related to regular frequency and how that's related to period and that sort of thing. Remember, the period is the amount of time it takes to complete one cycle. So if you're talking about a pendulum, it's you pull the pendulum up to its max point and you let it go. So you start the time and then you stop the time. That's one period. Or You could go start the time when it's hanging straight down, stop the time. That's the period as well. So all of that stuff is the period, and that's what we measure in seconds or whatever. And frequency is the number of cycles that happen in a single second, and it should make sense that frequency is 1/period. Now that we have that, we've got a little bit of understanding about the simple harmonic oscillator equation. Well, it turns out that that equation pops up in a lot of different ways. So let me first show you, for instance, if we consider a pendulum, a simple pendulum. So with a simple pendulum, you can imagine there's a pendulum whose length is L, and technically that length L is supposed to extend from the rotation point down to the center of the actual mass M, and then we imagine the actual string or whatever the mass is hanging on, the bob as we call it. We imagine that that mass is very very small compared to the other mass, so we can assume it's zero. And what we're going to do is we're going to say this angle right here is the amplitude of the oscillation. Its amplitude is out how far in radians or degrees you pull it out, and then you let it swing back and forth, back and forth. Now, the forces acting on this we know specifically are the mg, which is the weight, of course, but that can be broken down into components as follows. So, for instance, we can take and break this down into a component parallel to the pendulum rope, and then another one perpendicular to the pendulum rope, like this. And by symmetry, I think you can see that that's the angle theta here. And this quantity would be mg cosine theta, and this quantity would be mg sine theta. Now, there's also a tension acting on it along the string right here. And of course, that tension has got to be compensated for by being equal to mg cosine theta. But that equation, that particular aspect isn't that important to us. What we're going to use for this is the summation of the torques is equal to I times alpha, only alpha is going to be theta double dot. Remember, alpha is d2 theta over dt squared, or you could call it d omega over dt, where omega is equal to theta dot. So that's another thing we could use. Now, the big thing here is the torque is actually, in this case, because the mass is spinning this, or the bob is going down this way, that's actually causing a torque that's tending to make what we call clockwise rotation. And therefore, the torque is sort of pointing into the page. But uh, that tension is actually directly or is actually negatively related to the angle theta. So we actually are going to say that the torque is, instead of it being mg sine theta times L, it's going to be negative mg sine theta times L. So the torque part, the summation of the torques, is going to be mg sine theta times L, and I want to put parentheses around that so we don't think it's theta times L, and it's going to have a negative quantity. And the reason why it's got to be negative, as I said, is when theta increases, that's against the torque. So it's a restorative torque, in other words. Just like the F equals negative kx is a restorative force. When x gets bigger, the force points the other way. So if x is positive, then F points in the negative direction. Similarly, if theta is to the right here, which is sort of counterclockwise, if I treated the down axis as the x-axis, then the actual torque would be the other way. So with that in mind, we're going to set this equal to I, which for a point particle at the end of a length L is ml squared, and then that's equal to theta double dot. So what we have is negative mgl sine theta is equal to ml squared theta double dot. That sort of looks like a simple harmonic oscillator, but it's really not. In reality, it can only be a simple harmonic oscillator if that sine theta was not there. It would have to have a regular theta. And it turns out that the sine of theta is approximately equal to theta for small theta. And in fact, your book has it where it shows that even up to 30 degrees, sine theta in radians, when you actually use theta in radians, is only different from theta in radians by about 4.5%. So it's not as limiting as you might think. You can also realize that it comes from that because if you do a Taylor series expansion of sine theta, what you'll get is theta, and then the next term is minus one third theta cubed plus the next term is one fifth theta to the fifth minus dot dot dot. So you can see as theta gets bigger and bigger, the theta or as theta gets smaller and smaller, the theta cubed, the theta to the fifth, the theta to the seventh, all those are minuscule. So that's why we say sine theta is approximately equal to theta. Once I make that, then I can do a couple things. For one thing, I can see that the 2 exponent is going to cancel out with that L, and I can see that the M is going to cancel out with this. So in this case, I can now say the differential equation is going to be negative theta times G is equal to L times theta double dot. If I get them all on the same side and then try to divide by L, what I'll end up getting is theta double dot plus G over L times theta is equal to 0. And this is the simple harmonic oscillator equation. And that tells us in this case, omega is equal to the square root of G over L, where L is the length of the pendulum. So it turns out that when we actually do this for a pendulum, we get a simple harmonic oscillator equation again. And theta in this case, let me go ahead and write this in blue. And theta in this case is going to be theta equals theta 0 cosine omega t plus phi. So it's the exact same solution, except we instead of using an A, which would make you think of meters and stuff like that, we use the theta 0, which hopefully makes you think of radians or degrees. So that's the application of the simple harmonic oscillator to a simple pendulum. It turns out if you do it for a physical pendulum, then the equation is still very much the same. Only in this case, we got to do the same sort of process. So, what does the physical pendulum look like? Well, the physical pendulum looks like this. You're going to imagine a little point here, and here's a blob that's acting as a pendulum, and right here is the center of mass of the pendulum, and therefore we can imagine a little line like this and another little line like this. So this will be theta. And again, physical bodies act as if the forces act on just the center of mass, unless you're trying to consider how it's going to rotate. But as long as you're trying to figure out how it's going to move, then that's the case. So in this case, you're going to get again, this is mg. This is going to be mg sine theta, and this is going to be mg cosine theta. So again, we're going to get from the summation of the forces is equal to mass times acceleration. In this case, we're going to get negative mgl times, in this case, L is actually, I think we're going to use a H for this. So I'm going to say this distance right here from here to here, and that's the distance from the center of rotation of the pendulum to the center of mass. That quantity is going to be mgh times the sine of theta, and then that's equal to m times theta doubled, or excuse me, it's supposed to be equal to I omega. Sorry, I shouldn't even be writing as summation of forces. I did that a second ago. Oops. I wrote it up there properly, but for some reason I just jumped to summation of forces. So the summation of the torques is equal to I times theta double dot. That's what we're getting here. So the moment of inertia for this physical pendulum is going to be specifically, I just messed up my triple dots, my therefore symbol. Uh, Actually, I shouldn't even do therefore. I'm going to go ahead and erase that and go ahead and set it equal. So equal is going to be equal to the moment of inertia times theta double dot, and the moment of inertia is the moment of inertia of the physical pendulum rotated about that endpoint, basically, and that times theta dot. Excuse me, theta double dot. So in this case, if we assume let sine or let sine theta be approximately equal to theta, then what we're going to have is negative mgh theta is equal to I theta double dot. And in this case, we can go ahead and say theta double dot plus mgh over I times theta is equal to 0. And lo and behold, we have a simple harmonic oscillator equation again. So in this case, what we got is omega is equal to the square root of mgh over I. And additionally, we also have theta is going to be equal to theta 0 times cosine omega t plus phi. And in fact, there's several more instances there's at least two more that your book shows where the same mathematical apparatus applies because it's a simple harmonic oscillator. One of them, for instance, is a torsion pendulum. So if you let that tinsel stuff that some people hang from Christmas trees, it's sort of flat, a little bit wider than just regular string. It would be sort of flat and wide. If you let that hang down and then you have something hanging from it like this tied to it, if you let it go, eventually what's going to happen is that flat piece of tinsel is going to untwist and this thing's going to hang just like that. Now, if you give it a little twist of an amount theta, then that tinsel is going to try to bring it back and it's going to wobble back and forth like that. That's called a torsion pendulum, and it turns out that that has a another equation too, just like Hooke's law. In this case, the torque is equal to negative k times theta, and you say, okay, the left-hand side is going to be negative k times theta. The right-hand side is going to be I, the moment of inertia, times theta double dot. So that gives you yet another simple harmonic oscillator. An object going in a circle, that gives you another simple harmonic oscillator. So that's the key to what we're seeing here. The big thing is to remember how we can go about getting velocities and that sort of stuff. So for instance, we learned that the velocity, which was x dot, is negative a omega cosine omega t plus phi. And the way cosine is, it wobbles back and forth between positive 1, negative 1, positive 1, negative 1. So this x dot, which is the velocity, wobbles back and forth between a omega, negative a omega, negative a omega. And that implies, excuse me, that implies V max, the maximum velocity, is going to be equal to A omega. So that's another expression we can make use of. Similarly, we can say A of t is equal to x double dot, and that gives us negative A omega squared. Ooh, sorry about that. This was not supposed to be cosine. The part is right, but ooh, used too big of a eraser there. The front of it was right, but when we took the derivative of, and that should have been purple, when we took the derivative of cosine, we got negative sine. That's where the negative came from. So that should be sine. Now, if I take the derivative of this, we're going to get negative a omega squared cosine omega t plus phi. And again, cosine wiggles back and forth between 1 and negative 1, just like sine wiggled back and forth between 1 and negative 1. That's why I had V max is equal to A omega. So in this case, we can also see that A max, meaning the maximum magnitude of the acceleration, is equal to A omega squared, which also happens to be equal to V max times omega. So that's another set of equations we can use. When we go a little further, I'll go ahead and start showing you how to use initial conditions. But right now, I just wanted to get that out of the way. So with that in mind, I'm going to go ahead and jump to the first example in chapter 1, or excuse me, chapter 14, which is example 14.1. I'll probably go back to that page later and put that in. But here's example 14.1. It says car springs. When a family of four with a total mass of 200 kilograms step into their 1,200 kilogram car, the car's springs compress 3 centimeters. What is the spring constant of the car's springs, assuming they act as a single spring? And then B, how far will the car lower if loaded with 300 kilograms rather than 200 kilograms? So the first thing we need to know about this is we know specifically F in magnitude is equal to K times X. And X here is sort of the same thing as delta X. We sort of use those interchangeably when we're working with Hooke's law. So when I said the delta X was 3 centimeters, what I mean is I'm going to plug in X for the delta X in that X spot, and I'm going to plug in for the force. I'm going to plug in force is equal to weight is equal to mg. And in this case, it's going to be 200 kilograms times 9.80 meters per second per second. And when I do that math, I think it's 1960. We're going to say 200 times 9.8. Ooh, evidently, I got some crazy stuff going on my calculator. Hold on a second. I just started typing and it should have been fine, but it was not fine. So 200 times 9.8 gives me 1,960. And that's newtons. Okay. So for part A, what we're going to say is F is equal to KX gives me 1,960 newtons. Now we only had probably at best 2 sig figs there, so I'll underline those. That's equal to K, and then the X is going to be 0.030 because we really need this in the base units of the SI, and that means meters, kilograms, and seconds. So with that in mind, we see that K is equal to 1,960. I'm carrying the extra digits, in other words, newtons divided by 0.030 meters, and that gives me 6.53 times 10 to the fourth newtons per meter is equal to K. And notice I carried one extra digit because if I use this in a subsequent calculation, I really don't want it to be rounded to 6.5. I want to use one extra digit. So it's not like rounding twice. So that's part A. Specifically, they asked for what is the spring constant. Now in part B, they want to say, what if we hung 300 kilograms from it, or excuse me, what if we put 300 kilograms of people in there instead of 200 kilograms? Well, 300 people is 1.5 times 200 people, or 200 kilograms of people. So it's 3 halves, and F and X are linearly related. So if I double X, you expect the force to double, or if I double the force, you expect the X to double. If I increase the force by a factor of 1.5, then I expect the X to increase by a factor of 1.5. Since this was 3 centimeters, 1.5 of that should be 4.5 centimeters. So that's what we expect the answer to be, but I'm going to go ahead and work it out just to make sure. So here's the part B. We're going to say, okay, 300 kilograms times 9.80 meters per second is equal to 6.53 times 10 to the fourth newtons per meter times X. Therefore, X is going to be equal to 300 times 9.8 gives me 2940. So that's 2,940 newtons. And that's going to be divided by 6.53 times 10 to the fourth newtons per meter. And that's going to be divided by, that gives me 0.0450 meters. And that's our answer to part B. This is a very typical problem of what's done with anything with like F equals KX, Hooke's law or whatever, is they'll give you some data that you can use to determine K, and then they'll ask you, and they might not even ask you for K. They'll then say, okay, we know that when we put 200 kilograms of people in a car, the car drops down closer to the ground by 3 centimeters. how much will the car drop down when we put 300 kilograms of people instead of 200 kilograms? So they wouldn't even ask you the first part; they would just jump right into the second part. But that's the way that's done. Any questions on that? Okay. There is a conceptual example that they cover here, and basically they're saying, are any of these capable of causing simple harmonic motion? So what I'm going to do is I'll just draw a little line here, and the functions that they give us for possible simple harmonic motion, this is conceptual. Whoa, boy, this thing really messes up when it tries to do that. Conceptual example 14.2. So they said F is equal to negative 0.5 x squared. They said F is equal to negative 2.3 y. They said F is equal to 8.6 x. And they said F is equal to negative 4 theta. And they want to know which ones of these would actually cause simple harmonic motion. Well, if you put in x is positive in this first one, the negative 0.5 x squared, then you get obviously something stretching in the positive x direction, and the force is then in the negative direction. So it does try to pull it back. That feels pretty good. But what if we put in x as a negative number? Well, because it's squared, the negative number is not going to feed through, so I still get it pulling in the net and the negative direction. So if you push something to the negative, it's going to take off going even more negative instead of trying to restore it. So no, this one cannot be simple harmonic motion or simple harmonic oscillator. When I look at F equals negative 2.3 times Y, if I plug in a positive Y, I get F pointing in the negative direction. If I plug in a negative Y, I get F pointing in the positive direction. That to me is exactly what we need for simple harmonic motion. So I'll say this one demonstrates simple harmonic motion. So I'll put a check on it. If we look at the F equals 8.6 times X, if I put in a negative X, then I get the force in the negative direction, which makes it get worse. If I put in X in the positive direction, then I get a force in the positive direction, which also makes it worse. So this one's also a no. And then finally, when I say F is equal to negative 4 times theta, if I pull it out to an angle theta that is in the positive direction, then the F is going to pull it back because it's going to be in the negative direction. If I pull the theta in the negative direction, then F is going to be positive, and that's going to pull it back that way. So this one does match simple harmonic motion. So hopefully that makes some sense to you on that one. I don't know why I actually chose to write it there instead of where I did. I forgot I had already written this down here, but that's good enough. Uh, I'm going to go ahead on to the next example, which actually I wrote on the next page. Actually, no, this is a good time for me to stop and give you an idea of, let me see what the next example is for starters. No, let's go ahead and do. Yeah, that's nothing useful for there. So I'll just leave that part blank. We're going to go ahead and go to example 14.3. Example 14.3 says car springs again. Determine the period and frequency of the car in example 14.1a after hitting a bump. Assume the shock absorbers are poor so the car really oscillates up and down. As I normally tell my students here, watch Uncle Buck when he goes to drop the kids off at the school, and you'll see a good example of a car with bad springs in that he hits a bump and then like 3 minutes later it's still doing this number. So that's what we're talking about here. Now, what we learned from example 14.1 was what K was. We had learned, for instance, already that solution, we learned that K was equal to 6.53. Was it 6.53? Yeah, 6.53 times 10 to the fourth newtons per meter. And we learned that the mass of the car was 1,200 kilograms. And it said specifically, example 14.1a, I should put that A right here. And part A was when we were talking about 200 kilograms. So that meant the mass of the people was equal to 200 kilograms. Therefore, M total is equal to 1,400 kilograms. So what we're asked to find here is specifically Determine the period and frequency of oscillation. What we also know in terms of a solution is omega is equal to the square root of k over m. We also know that omega is equal to 2 pi f, and we also know that period is equal to 1 over the frequency. So those are what we're going to need. So let's start off with calculating omega. Omega is going to be the square root of 6.53 times 10 to the fourth newtons per meter, and mass is going to be 1,400 kilograms. So if I take 6.53 times 10 to the fourth and I divide that by 1,400, that gives me 46.64. And that is newtons per meter divided by kilogram. Now, a newton is a kilogram meter per second squared, so a newton per meter is just a meter per second squared. And then you divide that by a kilogram, or excuse me, it's just a kilogram per second squared, and you divide that by kilogram, I just get seconds squared in the denominator. So that's seconds to the negative 2 power. Now I'm going to take the square root of that by raising it to the 0.5 power, and that's going to give me 6.83 radians per second is equal to omega. They did not ask us for the angular frequency. They asked us for the frequency. And what we see is the frequency is equal to omega over 2 pi. And I'm going to use some units in the 2 pi to help you understand why this formula is the way it is. What we have here is omega is equal to 6.83 radians per second, and then 2 pi can be thought of as the number of radians per cycle. So, for instance, the cycle would be, in the case of a circular motion, the cycle would be a completion of 2 pi radians. So, in that sense, you can think of 2 pi as measured in radians per cycle. And now you can see that I'm actually converting radians per second to cycles per second, which is hertz. So, I'm going to take the 6.83 and I'm going to divide that by 2 times 3.14159, and that gives me 1.09. And that's in hertz. So that's our frequency in hertz. And of course, the period is equal to 1 over the frequency. So that's 1 divided by 1.09 hertz. And flipping that over by raising it to the negative 1 power gives me 0.920 seconds with one extra sig fig. So that's what the period is, 0.92 seconds. Any questions on that one? Now, this next one's kind of cool. In reality, if you just see something doing this kind of motion, it's repetitive, then why not think of it as like something times a cosine function or something times a sine function? It's acting like what we call simple harmonic motion, which is really just another word for sinusoidal motion. And sinusoidal means it behaves like the sine function or the cosine function. The only difference between sine and cosine is they've been shifted left or right. So they really are identical functions, just a matter of a left shift or a right shift. So now example 14.4, it says spider web. A spider of mass 0.30 grams waits in its web of negligible mass. A slight movement causes the web to vibrate with a frequency of 15 hertz. That's a frequency in hertz, so that's an F there. A, estimate the value of the spring stiffness constant K for the web, and B, at what frequency would you expect the web to vibrate if an insect of mass 0.10 grams is trapped in addition to the spider? So this is like the people being in the car in addition to the car. So the total mass is what's going to matter for that part B. So solution, what we need for this is omega is equal to 2 pi f, and omega is equal to the square root of k over m. And that's specifically all we're asked for is like the frequency and the spring constant, that sort of thing. So for part A, we're asked to figure out what the spring constant is. So I'm going to say omega is equal to the square root of k. Oops, that's really bad. omega is equal to the square root of k over m, which if I squared that, that would become omega squared is equal to k over m, and that tells us that k is equal to m omega squared. But we know that f is equal to 15 hertz. Therefore, omega is equal to 2 pi f gives us, if I take 2 times 3.14159 times 15, I get 94.25 radians per second. There's the units. And we only had two sig figs, so those are extra. So I now have F or excuse me, I now have omega. So now I can say K is equal to 0.30 times 10 to the negative third kilograms. Notice they gave us the mass in grams. I've got to use the mass in kilograms. So it's going to be K is equal to M omega squared, and omega is 94.25 radians per second, and I got to square that. So I'm going to square this 94.25, and now I'm going to multiply that times zero point 0.3 times 10 to the negative 3, and that's going to give me 2.67 newtons per meter. And you can see from that, it's a kilograms times a radian squared divided by a second squared. But a radian is just a pure number, so it's kilograms per second squared. But a newton is a kilogram meter per second squared. So if you divided a newton by a meter, you'd get kilograms per second squared, which is exactly what we have. And that's why this is newtons per meter. So that's the spring constant for the spider web. Now for part B, they want us to say what would the frequency be if there was an additional bug in it. And in that case, we're going to go ahead and work it out. We'll say for part B, oops, that was supposed to be a green marker. Come on now. Okay, for that case, why did I say it was green? It's supposed to be blue, crackhead. Okay, so B, in this case, we have omega is equal to the square root of K over M. And we're going to assume the K is the same, but we also have omega is equal to 2 pi F, and F is really what we're looking for. So that means F is equal to omega over 2 pi, which equals 1 over 2 pi times the square root of K over M. That's what we're going to use. So the frequency is going to be equal to 1 over 2 pi times the square root of 2.67 newtons per meter. Oops, newtons per meter. And now I'm going to have to divide that by the new total mass, which is 0.40 times 10 to the negative third kilograms, like that. So 2.67 divided by zero point 0.4 times 10 to the negative 3 gives me 1 over 2 pi times the square root of 6,675. And that is a newton per meter, which is a kilogram per second squared divided by a second, divided by a kilogram. So that gives me seconds to the negative 2 is the unit there. I'm going to take the square root of 6,675 by raising it to the zero point 0.5 power. And now and that's 81. And now I'm going to divide that by 2 pi. So I divide it by parentheses 2 times 3.14159, close parentheses. And that gives me about 13.0 hertz is equal to the frequency with the bug. Okay, so you see the heavier mass made the frequency go down. So what would have been like this, say, when the bug gets in it, it'll go maybe like that. And obviously, a spider could sense that and say, "Oh, well, I must have something in my web," and and go eat that bug. Any questions on you like sound effects? Any questions on that, Sam? All right. now we're going to go to something that I've already, all these things I've derived the equations for already by talking about those differential equations. So we're going to go to example 14.5 now, and it says a vibrating floor. A large motor in a factory causes the floor to vibrate at a frequency of 10 hertz. The amplitude of the floor's motion near the motor is about 3 millimeters. Estimate the maximum acceleration of the floor near the motor. Now, this is a really actual engineering type problem. If you walked into a facility and they had a motor like that and it was causing a vibration and you could measure that frequency and you could measure that amplitude, which obviously could happen just by filming it. And then when you filmed it, you could, measure the screen and all that sort of stuff and stop and start the time so you could see the actual amount of seconds that went by between it going from peak down to peak up to peak down again. That would be the period. And by doing that, you could figure that out. And then doing that, you could actually figure out what the acceleration is just by knowing how simple harmonic oscillators behave. Once you have that acceleration, according to Newton's law, Newton's second law, if you multiply the mass of the wood along with the motor and all that stuff and multiply that by the acceleration, that tells you exactly how strong that floor truss needs to be, for instance, or floor joist needs to be. So you could then design a solution to make sure the floor maybe stop doing that, or at least make sure it was secure enough nothing bad to happen. So that's what we're going with here. Our solution is going to be what we know is in this case, we are given, oops, I'm writing in the wrong place. I was like, none of these numbers make sense. I don't understand. So we've got the acceleration and all that stuff, but they're asking for the maximum acceleration. What we know is A max is equal to A omega squared. We learned that earlier. So all we have to do is write 3.0 times 10 to the negative third meters times omega, and omega, of course, is 2 pi times f, so that's going to be 2 pi times 10 hertz. And then that has to be squared. So what we're going to do is say 3 times 10 to the negative 3 times parenthesis 2 times 3.14159 times 10 close parentheses, square that parenthesis, and that gives us 11.8 meters per second, and therefore we now know the maximum acceleration that the floor is going to get, and therefore we also know the maximum force that the floor needs to be able to support by just multiplying that by, in some sense, some measure of the mass of the floor plus the actual motor that's causing the vibration, that sort of thing. Any questions on that? All right, now we're going to show you how to sort of look at a solution and sift out what the variables are. Example 14.6 says, starting with x equals a cosine omega t. The displacement of an object is described by the following equation, where x is in meters and t is in seconds. X is equal to parenthesis 0.30 meters, close parenthesis, times cosine, parenthesis 8.0 t in radians, close parenthesis. So what that means is the 8.0 times t spits out radians. That also implies that the 8.0 must be in radians per second, because if you have to multiply 8.0 times t, and you know t is measured in seconds, and you get out radians, then obviously the t being seconds, the 8 has to be radians per second. So now we can start off with that. Remember, the equation is specifically x is equal to a cosine omega t plus phi. And we see from this that clearly phi is 0. Okay, that's one thing, but they didn't ask us that. But that's clearly one thing. The a has to be whatever's multiplied by the cosine, and it should have units of meters, and all this matches, so that makes sense. So for part A, I'm going to say a is equal to 0.30 meters. And then for part B, This one's a little more complicated. For part B, we need to remember that omega is equal to 2 pi f, and that omega is going to be equal to 8.0 radians per second. We recognize it because it's multiplied by the t. And that's enough, but it also confirms because I worked out that the 8.0 must have units of radians per second, which is exactly the units that omega should have. So that gives me a little bit more confidence. With that being said, we can therefore say that F is equal to 1 over 2 pi times radians, or excuse me, times 8.0 radians per second. So with that in mind, we can say that F is equal to 8.0 divided by parenthesis 2 times 3.14159 close parenthesis. That gives me 1.27. And that's 3 sig figs, and they really only gave us 2 sig figs on everything. So that's extra. So F is equal to 1.27 hertz. We've got that down for part B. And this is part A. Now, for T, the period. The period is given by 1 over the frequency. So in this case, I'm going to raise that frequency that I just got to the negative 1 power. And when I do that, I get 0.785 seconds is equal to the period. So I can box this off, and that's answer to part C. Part D, they want to know V max, and we know exactly how to do that. So D V max is equal to A omega, and that's equal to 0.30 meters times omega, which we already found out was 8.0 radians per second. So that's going to be 2.40 meters per second is equal to V max. Now, part E, we want to know A max. A max is equal to A omega squared, but you can also say that's V max times omega. That's the way I'm going to use it. So I'm going to say it's 2.40 meters per second times 8.0 radians per second. And 8 times 2 gives me 16, and 8 times zero point 0.4 gives me 3.2, so that should be 19.2. And that's meters per second is equal to A max. And that's part E, just like this was part D. Any questions on that? So example 14.7 is a very similar one. This says loudspeaker. The cone of the loudspeaker in figure 14.9 oscillates in simple harmonic motion at a frequency of 262 hertz, which is middle C. The amplitude of the central part of the cone is A equals 1.5 times 10 to the negative fourth meters, excuse me. At t equals 0, x is equal to a. So this is an initial condition type situation. They just given us an initial condition. At t equals 0, x is equal to a. So that would allow me to plug in t equals 0 into x equals a cosine omega t plus phi. And in principle, we might be able to figure out what phi is and what a is. But with only that one condition, we can't necessarily do it because there's two unknowns. For part A, they're asking what equation describes the motion of the center of the cone, and then B, what are the velocity accelerations as function of time, and C, what is the position of the cone at t equals 1.00 meters milliseconds. So that's the types of question we're trying to answer here, and it oscillates at simple harmonic motion at a frequency of 262. The amplitude of the central part is x equal. So if x is truly the amplitude A, they're actually telling us A is the actual X value, which is the 1.5. So we already know exactly what the A is. So that tells us solution X is equal to A cosine omega t plus phi, like that. And specifically, we know A is equal to 1.5 times 10 to the negative fourth meters. So we can now say that X is equal to 1.5 times 10 to the negative fourth meters times cosine omega t plus phi. Okay. Now we can say, for starters, omega is equal to 2 pi times f, and we know f is 262 hertz, so that's 2 pi times 262 hertz. So 262 times 2 times 3.14159 gives us a really big number. It gives us 1,646 radians per second is equal to the actual angular frequency. And we really only had, in that case, we had 3 sig figs. So this 6 is not really a sig fig. But now that we have that, we can say X is equal to 1.5 times 10 to the negative fourth meters times cosine of 1,646 radians per second times t plus phi. And because of that, we can now evaluate the fact that at t equals 0, x is equal to a. So at t equals 0, x is equal to a implies I'm going to say a, which equals 1.5 times 10 to the negative fourth meters, is equal to 1.5 times 10 to the negative fourth meters times cosine of phi, because it was cosine of omega t plus phi, but we said it's at t equals 0, so the omega t goes to 0. This tells us that the cosine of phi must be equal to 1, and the cosine of phi is equal to 1 at phi equals 0. It's also 1 at phi equal 2 pi. So we could say phi equals 0 or plus or minus 2 pi or plus or minus 4 pi, so on and so forth. None of that is particularly helpful. We might as well just use the 0. So now I can finally say for part A, x of t is equal to 1.5 times 10 to the negative fourth meters times cosine 1646 radians per second times t. And that's the whole argument of the cosine function. So that's the answer to part A. So what you saw there was a little microcosm of how you interpret initial conditions. You literally just say, here's my x equals a cosine omega t plus phi. Here's the value at t equals 0. Plug that on the left hand side, plug in 0 t equals 0 on the right hand side, and hopefully you can figure it out. In this case, because they told us a specifically, we already knew a, that allowed us to go ahead and determine phi as well. So we're done with that. Now for part B, we want v of t and a of t. V of t is equal to x dot, and we can see that that's going to be negative a omega sine omega t. So this is going to be a negative times 1.5 times 10 to the negative fourth meters times omega, which is 1,646 radians per second times the sine of 1,646 radians per second times time, like that. Now we need to go ahead and figure out what that number is in front of all this stuff. So 1.5 times 10 to the negative fourth times 1646 gives me 0.2469. So I'm going to say V of t equals negative 0.2469 meters per second times the sine of 1,646 radians. That's really some bad looking radians here. Radians per second times t. And that's our velocity as a function of time. The acceleration as a function of time, a of t, is equal to x double dot, which is also equal to v of t with a dot over it. So I'm just going to take the derivative of this. That's going to be negative 0.2469 meters per second times the omega, which is 1,646 radians per second, times this time, when we take the derivative of sine, we get cosine, and that's still 1646 radians per second times t. So now I'm going to take the 0.2469 and I'm going to multiply that by 1646, and that's going to give me 406. So A of t, A of t is equal to negative 406.4 meters per second times cosine of 1,646 radians per second times t. That's our acceleration. And then finally, what they want to know is what is x at 1 millisecond. So we're going to do that as follows. X of 1.00 milliseconds is equal to, we already had that it was 1.5 times 10 to the negative fourth meters times cosine of 1,646 radians per second times 1.00 times 10 to the negative third seconds. Now, that 1646 times 1 times 10 to the negative third is going to be 1.646, but that's in radians. So you either got to put your calculator in radian mode and then compute it, or what I'm going to do is take the the 1.646, and I'm going to convert that to degrees, and then I don't have to change my calculator mode. And so doing, this is what we get. So I'm going to say cosine parentheses 1,646 times 1 times 10 to the negative 3 times. Now, that's radians, so I want to multiply that by 180, and then I want to divide it by pi. So I'm going to say times 180 and then divided by 3.14159. So I'm basically taking the cosine of 1,646 times 1.00 times 10 to the negative third times 180 divided by 3.14159, and that gives me the cosine is equal to negative 0.0751. So just to make sure you can verify this yourself at home, this is negative 0.07513 is the answer for the cosine. Now I'm going to multiply that by 1.5 times 10 to the negative fourth, and that's going to give me specifically negative 1.13 times 10 to the negative fifth meters is equal to x of 1.00 milliseconds. So that's our answer. Now you could have also changed your calculator mode to radians and just put that in, but either way, it should give you the same answer. And let's see what your book got. Negative 1.2 times 10 to the fifth. I'm off by a little bit in the decimal place because I got negative 1.1. They got negative 1.3, but everything else looks about the same. But I did carry an extra digit. They rounded the 1646 to 1650, so they're rounding and then they're rounding again. I don't believe in doing that. I like to keep the whole number till the very end. So that's why I carry the extra digit. Any questions on that one, Sam? All right. Now we're going to example 14.8, and this is sort of a hodgepodge of everything that could possibly be done. It says example 14.8, spring calculations. A spring stretches 0.150 meters when a 0.300 kilogram mass is gently suspended from it, as in figure 14.3b. The spring is then set up horizontally with the 0.300 kilogram mass resting on a frictionless table, as in figure 14.2. The mass is pulled so that the spring is stretched to 0.100 meters from the equilibrium point and released from rest. So, release from rest is giving you an initial condition. Release from rest means that V at t equals 0 is 0. And the fact that you told it that we stretched it to 0.100 meters means they're also giving us initial condition x of 0 is equal to 0.100 meters. So that's actually them giving us the initial conditions. Remember, I told you when you're given a differential equation, if it's a first order differential equation, you're going to have one constant of integration if you were integrating it. So you're going to have one variable in the function that you use as a test solution that's going to have to be determined from the initial conditions. This would allow you to do one of those. But in this case, they gave us two because this is a second order differential equation and our unknowns are a and phi. So giving us two equations should give us enough to figure out both a and phi. Now, with that in mind, let's go ahead and move on. So part A says, determine the spring stiffness constant K and the angular frequency omega. B, the amplitude of the horizontal oscillation A. C, the magnitude of the maximum velocity Vmax. D, the magnitude of the maximum acceleration A max of the mass. C, the period T and frequency F. And E, the displacement X as a function of time. And G, the velocity at T equals 0.150 seconds. So solution here, we're going to make use of the fact that X should be equal to A cosine omega T plus phi. We're also going to make use of the fact that omega is equal to the square root of K over M. And we're going to make use of the fact that omega is equal to 2 pi f. We're also going to make use of the fact that x of 0 is equal to 0.100 meters and that v of 0 is equal to 0.00 meters per second. So those are some of the initial conditions and some of the equations I'll be needing, so on and so forth. We're also going to use the fact that V is equal to X dot and that A is equal to V dot, which is equal to X double dot. So let's start off with part A. A, they want to know the K. So in this case, we've already figured out that the stretch of the spring, that's another equation we need. F is equal to kx, which would normally be a negative, but we're just trying to use it to find k. So in this case, we're going to say k is equal to F over x, which equals, in this case, it's 0.300 kilograms times 9.80 meters per second, and then all of that is divided by 0.150 meters. So zero point 0.3 times 9.8 is 2.94, and now I'm going to divide that by 0.150, and that gives me 19.6. So K is 19.60 newtons per meter is equal to K. And omega, of course, is omega is equal to the square root of K over M. So that's 19.6 newtons per meter. I should go ahead and write that zero in there just so you'll know I'm carrying the extra digit that's not a sig fig. So 19.60 newtons per meter divided by 0.300 kilograms gives us 19.6 divided by zero point 0.3 is 65.333. And now I'm going to take the square root of that by raising it to the zero point 0.5 power. And that gives me 8.083 radians per second is the angular frequency, and that's one extra digit that I'm really allowed. So that's the angular frequency. I know it's hard to read, but that says radians per second. So I've now gotten the omega and the K, which is part A. Now, part B, they wanted us to give you the amplitude, and we already know specifically the amplitude is the maximum stretch it's going to be. And because they stretched it to A, which is 0.100 meters, and released it from rest, they didn't give it any initial velocity. If they gave it initial velocity in the positive direction, then when it got to negative A on the opposite side of the equilibrium point, it would have went a little further because it was given a little boost. But that's all it's going to do is just go up to the same one since it's a frictionless table. If it wasn't frictionless, it would be even less than zero point 0.1. So we can automatically say that A horizontal is equal to 0.100 meters. And that's part of just understanding what they're saying here. Now for part C, they want to know Vmax, and Vmax is equal to A omega. So in this case, I'm going to say 0.100 meters times 8.083 radians per second. And that gives me 0.8083 meters per second is Vmax. I'm not going to write equals Vmax because we've got a lot of stuff to fit in here, but that's part C. So I'll put that there, and this is part B. I'll put that there, and this is part A, and this is part A. So that keeps track of it. So 0.8083 is Vmax. Now we're going to see what part D is. I actually might be jumping the gun. I'm a little worried about not having enough room because it's so much stuff here. But I think I've squished it enough already. So for D, we are specifically asked for Amax. And Amax, as we learned, is equal to A omega squared, but it's also equal to Vmax times omega. So I'm going to say 0.8083 meters per second times 8.083 radians per second. So if I multiply this 8.083 that I had for omega times 0.8083, that's going to give me 6.534, or excuse me, 6.533. Oops. 6.533 meters per second is equal to Amax. So that time I just boxed it off and I was able to put the variable that it's equal to there. And that, of course, is part D. So I'll go ahead and do that as well. So now we've got part D. We want now part E and part E. I want T and F. So to do that, I'm going to say E. Specifically, omega is equal to 2 pi F. So F is equal to omega over 2 pi, which is 8.083 radians per second divided by 2 pi radians per cycle. Again, you don't have to write that. It's just hopefully you're learning something about it by me writing that, and that's the whole purpose of it. So I'm going to take 8.083 0.083 divided by parentheses 2 times 3.14159 in parentheses. That gives me 1.28. Carrying one extra digit would be 1.286. And that is in hertz. And that's the frequency. So we now have the frequency is 1.286 hertz. And the period t, of course, is 1 over the frequency. That's going to be 1 over 1.286 hertz. So I'm going to raise this value that I just got on my calculator to the -1 power, and that's going to give me 0.7773 seconds is equal to the period. Box that off, and that's answer to part E, and this is answer to part E as well. Any questions on that so far? Okay. Now for part F, they want to know x of t. So F, we have x of t is equal to a cosine omega t plus phi. We know x of 0 is just equal to 0.100 meters, and we know v of 0 is equal to 0. Okay, so we also know what omega is. So if we do that first initial condition, we're going to say 0.100 meters is equal to 0.100 meters times cosine of, in this case, it's going to be 0 plus phi. So it's just the cosine of phi. And again, this implies phi is equal to 0 r plus or minus 2 pi r plus or minus 4 pi dot dot dot. Obviously, we would go ahead and choose that being 0, but just as a double check, we want to say that v of t, which is x dot, is going to be equal to negative a omega sine omega t plus phi, like that. So if I put these numbers in, I'm going to get negative, and then a is 0.100 meters, and then omega is 8.083 radians per second, and then all of that is times sine of 8.083 t, just leaving the units off for a second, plus phi, like that. Now we can go ahead and compute zero point 0.1 times 8.083. We need that's zero point 0.8. So we end up getting this is equal to negative 0.803 meters per second times the sine of 8.083 radians per second times t plus phi. So v of 0 equals 0 gives us 0 is equal to negative 0.8083 meters per second times sine of just plain phi. And if we chose phi equals 0, then that works. If we chose, oh, actually, if we chose phi is equal, no, if we chose phi equals 0, that doesn't work, does it? Yeah, the sine of 0 is 0, so that does work. So we can use that, and that tells us finally that x of t is in fact equal to 0.100 meters times cosine of 8.083 radians per second times t in square brackets like that. And that is x of t that we were asked for part F. Now for part G, they want us to know the velocity at 0.150 seconds. So G, velocity at 0.150 seconds is equal to, we already worked out what the velocity was. We got negative 0.8083 meters per second times the sine of 8.083 radians per second times 0.150 seconds. That's all in radians again. So I'm going to do that same thing. 8.083 times 0.150. That gives me 1.21. I'm going to multiply that 1.212. I'm going to multiply that one by 180 and divide by pi. So times 180 and then divide that by pi, 3.14159. That gives me 69.46 degrees. That's just in case you wanted to know what the what that conversion gave us. So now I take the sine of that. Oh, something just happened to my calculator. Hold on a second. Okay, I'm going to take the sine of the answer I just got, and that gives me 0.936. Now I'm going to multiply that 0.9365 times 0.8083 times negative 1, and that's going to give me negative 0. Oops, wrong color. That's going to give me negative 0.7570 meters per second is equal to V of 0.150 seconds. And that is the same thing your book got as well. So we did all that. That is part G. Any questions on that, Sam? All right. Now, what I want to show you is something about that mass on a spring. I want to talk to you about it in terms of energy, and then we can make some sense out of that. And I also wanted to show you a more general form of the initial conditions. So let me start off with the initial conditions. They're called initial conditions because often they give us some information at t equals 0. But to be honest with you, you could use t at any time, but we are distinctly only considering at t equals 0. So, for instance, x of t equals 0, which is technically x of 0 seconds. If we called that x0, that would be one initial condition. So I'm going to say equation 1. And then we could say V of t equals 0 is equal to V of 0 seconds. And we're going to call that just plain V0, and that's a second initial condition. Now that we have those two initial conditions, we can use those to figure something out. We know that x of t is supposed to equal a cosine omega t plus phi. So combining this and 1, we get x0 is equal to a cosine phi, and I'm going to call this equation 3. We know that v of t is equal to negative a omega sine omega t plus phi, and if we combine equation 2 and this, we get V0 is equal to negative A omega times sine of phi, and we're going to call that equation 4. So if I divide equation 4 by equation 3, then I get the following. V0 over x0 is equal to negative A omega sine phi over A cosine phi, which gives me negative omega tangent phi. So that tells us the tangent of phi is actually equal to negative V 0 over omega times x 0. Notice omega times x 0 has the same units of velocity, so that works out okay. Now, what do we have to do? Well, we can imagine a right triangle that has an angle negative phi, for instance, and this is the angle phi right here. This side is the opposite, so I'm going to call that V0. This side is, it's actually negative V0, and this side is the adjacent, and that's omega times x0, and that means the hypotenuse has to be equal to omega squared x0 squared plus V0 squared, like that. So with that drawing, we can now figure out what cosine is and what sine is. So if I now look at equation 1, we have, well, not equation 1. If I now look at, we got phi. If I plug this back into, for instance, equation 3, let's try that. 3 says x0 is equal to a cosine phi, but according to this, cosine phi is adjacent over hypotenuse, and that would be, this is x0 equals, I left off the equals. Therefore, I'm going to say x0 is equal to a, and then in place of cosine, it's omega x0 is the adjacent. The hypotenuse is the square root of omega squared x0 squared plus v0 squared, like that. And that tells us that a is specifically equal to, notice the x0 cancels out on both sides. A is specifically going to be the square root of v0 squared plus omega squared x0 squared divided by omega. So we now have determined both phi and a. We didn't actually explicitly state it, but phi is going to be equal to the inverse tangent of negative v0 over omega x0. So this is an actual general solution for what A and phi are for a simple harmonic oscillator. Once you know what omega is, once you know x0, and once you know v0, you can immediately use all these to determine what A and omega, or what A and phi are. So that's one way. I've already showed you the initial conditions when x was equal to A at t equals 0 and v was equal to 0 at t equals 0. Your book does another one where x is equal to 0 at t equals 0 and v is equal to some velocity at t equals 0. And you can see that in your book as well. But that's the main thing. And that's a big part of differential equations. It's not only that you have to solve the differential equation by sometimes just guessing at a solution and then plugging it in and seeing what happens. Other times they give you very prescriptive methods, algorithms, and whatnot that you can use to get it. But once you're done with that, you still don't have the solution because you're going to have to introduce one constant for every order of derivative you have. So if it's a first order differential equation, that means the highest order derivative is a first order derivative. If it's a second order differential equation, that means the highest order would be a second order derivative. And a first order derivative means you're only going to have one constant. A second order differential equation means you're going to have two constants. A third would be three constants, and so on and so forth. So you always got to do that part as well. So there's our initial conditions evaluation. Now, I want to tell you that we can work all this in terms of energy. So let's look at energy. And with energy, we know that E is equal to U plus K. If we're talking about a mass on a spring, then we know K is equal to 1 half mv squared if we can assume the mass of the spring is negligible compared to the mass on the spring. And we know U is equal to 1 half K x squared. So E is equal to 1 half m v squared plus 1 half k x squared. Well, we also know x is equal to a cosine omega t plus phi, and we also know v is equal to a omega times negative 1 times the sine of omega t plus phi. So we can say E, by the way, in addition to E being U plus K, we know that when the spring is maximally extended or maximally compressed, either way, the actual X is A, the amplitude. So in one case, the energy can be said to be 1 half K A squared. But in another case, if you consider when the mass is blowing through the equilibrium point, at the equilibrium point, the X is zero. So the potential energy is zero, and all of the energy in that case is kinetic energy, in which case you have 1 half mv max squared. So those are two different ways you could actually address the energy. You could say the total energy is 1 half K A squared, or you can say the total energy is 1 half M V max squared. But you can also say E, whichever one of those you wanted to do, you could put on the left. But right now I'm just going to put E. E is equal to 1 half K. Now X is going to be, it's going to be X squared. So it's 1 half K A squared cosine squared omega t plus phi, and then plus kinetic energy. So that's 1 half m. And now V is going to be negative A omega sine omega t plus phi. And I'll make that into a square bracket, and that's going to be squared. So I get 1 half K A squared cosine squared. I'm not going to write the argument right now. Plus 1 half M a squared omega squared sine squared. Again, not going to write the argument. That looks pretty nice, but if we remember, omega squared is equal to k over m. If I do that, then I'm going to get this result. E is equal to 1 half k a squared cosine squared of the argument plus 1 half m a squared. Now omega squared is k over m, and then I've got the sine squared there. You can see that the m is going to disappear here, and I have now a common factor of 1 half k a squared, so I can write this as 1 half k a squared times cosine squared argument plus sine squared argument, which is just equal to 1. Because of that, we see, like I said, the energy is 1 half K A squared. Similarly, we can say E is equal to 1 half K A squared cosine squared plus 1 half M. Uh, in that case, we had A squared omega squared times sine squared. But in this case, we can remember that V max, we can remember that V max, or actually just V. No, I don't want to do that way. I already substituted the omega to get rid of K. Oh, I can say K is equal to M omega squared and apply that here and here, and I get E is equal to 1 half. And now in place of K, I'm going to write M omega squared. The A squared is already there, and I got the cosine squared of the argument plus 1 half M omega squared, or excuse me, A squared omega squared. and then sine squared, the same argument. Now you see I have a common factor of ma omega squared. So in that case, I'm going to write equals 1 half m a squared omega squared times cosine squared plus sine squared. This is again equal to 1. And not only that, V max is equal to A omega. So I can finally say this is 1 half M V max squared. So now I've told you exactly what we believed based on the physical manifestations of the problem. I've now shown it with these equations. Because of that, you can go ahead and do write equations to get the x at any point in time or get the velocity at any point in time, given certain conditions. Specifically, we can have, for instance, since the total energy E is equal to 1 half K A squared, but that's also equal to uh, 1 half mv squared plus 1 half K x squared, we could use that to figure out what the actual velocity is. And when we do it, we'd find that v is equal to plus or minus the square root of k over m a squared minus x squared. So this is a neat new equation that we can use to find out, for instance, the velocity if we know the stretch of the spring. If we know how much the string is stretched or compressed, i.e. the quantity x, then we can figure out what the velocity is. Not only that, you could call this, you could say v is equal to plus or minus v max times the square root of 1 minus x squared over a squared, which I think y'all can easily see how both of these equations came to be. I want to circle that in a red box. I think you can figure out how both of those came to be. And that's about it. So these gives you some extra tools to work examples 1410, 1411, that sort of thing. So use for examples 14. I think the last one we did was 8, right? Yeah, 14.8. So we can use stuff like this for 14.9, 10, and 11. I think the 9 is one of them. But that's it. We've actually covered all that I was really wanting to get through. I've already shown you how you can apply these methods to the case for a simple pendulum and for a physical pendulum. That means I'm not going to do anything for the circular motion. I'm also not going to do anything for the torsion pendulum. And if you're looking at the subsections, that means in chapter 14, I am skipping part of 14.6, all of 14.4, so I'll just write it right here. Skip part of 14.6, but we're also skipping 14.7 and 14. By the way, this is just part of in the 14.6 case. We're skipping 14.7 and we're skipping 14.8. That means I'm not going to ask you any exam questions on 14.6, 14.7, well, part of 14.6 specifically. I'm not going to ask you any torsion problems from 14.6. I'm not going to ask you anything about 14.7. I'm not going to ask you anything about 14.8. Tomorrow at 8 during our lab time, I will cover chapter 15, again in abbreviated form, and those notes will tell you specifically what parts I'm going to skip. I'm going to attempt to make a new practice test other than the one that's already been put up and I fixed and everything. I'm going to try to gear down to chapter 14 and chapter 15 to the stuff that's relevant, and I'll make a new one. But what that's going to mean is if you've already managed to get 100 on that practice test for the final exam that's already up, then you've got your 100 for the extra credit. So don't worry about getting 100. But as soon as I make this other one, you want to start taking that to prepare for the test. You don't want to mess with the original one because that has a lot of stuff from 14 and 15 that's not required. Additionally, I'm going to try to make a chapter quiz for chapter 14 and a chapter quiz for chapter 15 that just includes the parts of 14 and 15. I will send announcements as each of those are done. But as I said, you guys can take your tests on Monday. You can take it on Tuesday. You can take it on Wednesday. You can take it on Thursday. Ideally, if you're going to take it on Friday, I want you to take it by noon on Friday, meaning I would ideally like you to finish by noon, but at least take it by noon so that I could imagine you being done by like 2:30. Okay. Uh, any of those days, you're welcome to take it. If anybody's planning on taking it on Monday, you might want to let me know because my intent is not to have it all ready until Tuesday because I got all these other things I got to do, including grading the rest of your labs, which I'm grading really nicely, by the way. So just keep that in mind. You're free to go, and if you show up tomorrow at 8, I'll see you. If you don't, that's okay. You don't really have to. I will use that to cover what I think is relevant for chapter 15, and I'll also use that as a Q&A session. It's supposed to be, 2.5 hours with me. I don't think I'll need the full 2.5 hours to cover the part of 15 that I want to. So there's certainly Q&A time. I can also book a Q&A on Friday. If someone text messages me and says they'd like a Q&A on Friday, I can set up a Zoom meeting, and then if it fits in my schedule, I'll set that up, let that student know, and then I'll let all the other students know. I could possibly do it on a Saturday or Sunday, but then again, I'm also having one on Monday that's actually at JC or in the J building, the science building on the Virginia Beach campus, and I'm doing that from 9 to 10 in the morning on Monday. I'm doing it again from 9 to 10 a.m. on Wednesday, and possibly I could do some other times. So let me know if any of those things interest you or if you need any help. You can always, of course, text me or email me, but texting is quicker. Thanks, Sam, for coming. Chat me your first and last name just so I have you there. But you're free to go, bud. We're actually out a little bit early, so if you have any questions, you can stick around and I'll certainly answer them. All right. I think Sam might not be there anymore. He might have lost his internet connection or whatever, but that's okay. Wasn't required to be here anyways. No big deal. So thanks for coming, everyone. I will see you next time. Bye bye.